Okay, so I don't have a prepared talk about the optical table software, but I have, on GitHub, I have the optics documentation, so I can just go through that documentation. This is the MEDM display for the table record that supports a 6 degree of freedom optical table, where they have 3 Y motors, vertical motors, and then typically 3 other driven motors. In this case, these 2 motors can drive the table, can rotate the table about the vertical axis, and this guy can drive the table in Z. And then the Y motors are responsible for rotations about the horizontal axis, either like this or like this. And did you have specific questions about this?
So I have a geometry, it's called trisphere, and they have a specific arrangement of the motors, which I don't have a drawings right now. So it's like two motors in line and then one opposing.
It sounds like the car's geometry.
And there's 3 Y motors that just go up and down. But I don't remember.
So that sounds like the geocar's geometry.
Maybe something like this, yeah. So 3 motors vertical jacks, and then there are free motions, so they can slide appropriately. And then spring loaded for the. So when they assemble the slides, it's not constrained. Slides are always vertical. And they basically, when jack goes up, the other axis can slide freely.
Mm-hmm.
So this is this would be maybe similar to this. So you have 3 motors. You have 6 motors.
In this case, there are 6 motors. There are
6.
3 Y motors that are represented by these dots,
Okay.
and then there are motors that move in the horizontal plane, represented by these arrows,
Okay.
and then there are constraints in the horizontal plane,
Right. So
represented by this line.
So these will be sliders actually that you can.
These are
slide.
sliders, right. And this is a slider in both directions. This is completely unconstrained.
Okay.
And this is driven in both directions, completely constrained.
Okay.
And this is driven in one and also constrained in the other. So the question of whether or not you can use this software for a motor, for a table that might have this same geometry, is answered by whether or not the horizontal motions are, if you're interested in the horizontal motions, whether or not they are configured like this.
So where are the equations for this?
So the question is, where are the equations? And they are in the motor record, or the table record. In the optics module source directory is the table record, and they are messy,
Right.
right? Because this is a messy problem.
Well, 5 degrees is several pages in the formula.
No, it wasn't that much. MATLAB or Mathematica was able to crank that down to a couple, 2 or 3 lines. So, yeah, I wasn't able to solve it though. I mean, and there's another way to do this really. And the way people do hexapods that's pretty well documented, and there actually is, I think there might be hexapod software somewhere in the optics module that follows that prescription. And it's pretty useless to do that in an EPICS database because you need those kinematic equations evaluated continuously if you want to actually have the hexapod continuously instead of moving from point to point. So
There's interpolation for hexapod. It's not exact solutions, I think.
Well, yeah, at some level they're not exact, but they're not exact in the sense that calculus is not exact. Mm-hmm. They are doing these, evaluating these expressions in real time, point to point. And so even though it's not going to be a linear trajectory for anybody at any kind of a move, they nevertheless are going to get very close to the right speed and position with a kinematic-based solution. It's matrix-based. And that's probably what I should have done here. But after I wrote that, I wasn't willing to go through there and rewrite it.
Yeah, because I was trying to solve the equations, and I was able to solve them in inverse kinematics was simple, it was closed form formula, but forward kinematics just blows up, and I think it cannot be solved exactly.
Okay.
It was pretty complicated.
I have a question. So, could you go over what is available in optics module that we can use?
Yes.
So, because I just want to explain the question. As you mentioned, there are like a virtual motors. I don't know whether it's here or in another place. Soft motors, where they're located. So, for our coordinated motions, we deploy our coordinated motions, even a simple one, down on the PMAC level with the forward and reverse kinematic, and it actually does not make much sense because of the database, especially the one that is already available, it's much more simpler to do. So it's good to know what is available so we can just grab and use it. Another question that you have, so here is, I'm looking at the optics module. Is it like a collection of databases that I can use, or need to build something in order for it to work, or just a little bit of overview, which can be very trivial for you, but it could be informational for us.
Okay, so the question basically boils down to, can I give like a summary of all the stuff that's in the optics module in the event that you guys might want to use that as opposed to programming something similar into a delta tau controller, which is sort of the default operation that you guys do. This stuff might be easier. So first of all, we have this monochromator, which is a 3-motor coordination. The rotation stage and the Y stage and the Z stage, they all have to move in synchrony. And this doesn't try to do that while it's moving. It doesn't try to, because these are the trajectories are like transcendental functions. And so the optics database doesn't have the smarts to do that in real time, but it can calculate the end position that it wants Y1 and Z2 and theta to go to and send them there at speeds that ensure that they arrive at the same time. That's as far as it is. So this is just a point-to-point coordination, not a coordination that is maintained while the motors are moving. So that's not going to be appropriate for a fly scan over any long distance, right? You would want to program that into a servo controller if you're worried about having that motion exact while it's moving. But it's appropriate for a step scan, and it's just as good, I would argue, as having it programmed in a controller for a step scan, because all you have to do is get there, and then you're going to take data, and then you move again and get there, and then sit there and take data. So that software exists for 2 different flavors of monochromators, and the difference is basically in how Y and Z motors are treated. And this is the user interface for that monochromator. You can specify energy or wavelength or theta. You can specify the Miller indices and the crystal constant. And you can specify what kind of silicon or diamond or whatever. And then this is how you make the thing move. And you can put it into different modes, a normal mode or a channel cut mode, where those 2 will just rotate. You can freeze Z independently or freeze Y independently. So there's some flexibility about how the user might want to make that thing move. There's another geometry, as I said, of the same basic design, high heat load monochromator. There is support for a high-resolution double crystal 4-bounce monochromator for milli-eV energy resolution. And it's a little bit complicated how this thing works, and I'm not going to go through the X-ray optics of it or anything like that, but from the user's viewpoint, it's pretty simple. They just want to give it, they want the energy. So that's how the actual motors work. These 2 guys in most implementations that I've seen, these two guys are actually fixed together, and these two guys are fixed together so that they rotate. These could actually be channel cuts, and originally they were. This was a channel cut, and this is another channel cut. But I think nowadays they're implemented more with independent stages, and this is the user interface for that, and it looks the same almost as the user interface for the high heat load monochromator, except now you have two crystal species, and you have two thetas, and you have one extra thing, is that because these things are so sensitive to the incoming beam, and because it's such a pain in the neck to tune this thing, if the incoming beam changes in angle a little bit, a user asks for the ability to change the orientation of the world, basically, of the whole thing, to match the incoming beam angle, and that is, you can specify that in microradians. So I think just to know that it exists, if you might want to use it, I know you guys, some of you guys have this monochromator. I'm sure some of you guys have this monochromator. And there is another flavor of this monochromator that I think Pete Siddons and Jerry Hastings were using for their Mossbauer work early on. And it's sort of the same kind of an idea, but a little bit different in implementation. So there's support in Synapse for that high-resolution monochromator as well, and it looks the same. It's basically the same kind of stuff with just different equations. And there is a spherical grating monochromator which has an entrance slit that can move and an exit slit that can move, and typically one of those slits is fixed. And then a grating, and you can choose one of several different gratings typically. And then that grating motor can move, and it has to be moved with pretty good precision in order to end up with a useful device. But it looks just like the other monochromators, right? It's energy wavelength and phi, but some differences because the spherical grating monochromator really, it keys on these input and output slits. And there is, I don't know if I have a description. Yeah, I do. There's a bunch of different gratings for some of these spherical grating monochromators, and users wanted to get a handle on them. So if they have a whole bunch of different strips on that, you're going to need to be able to move back and forth and then have the software respond to the new D-spacing, or what, it's not D-spacing, the grating, what is it called? Line density. And so this gives you, this is where the motor has to go in order to get that grating. I don't remember, I haven't worked on this for a long, long time. There is a multi-layer monochromator that I don't think has actually ever been used. I'm not sure. And again, it looks like a monochromator, it looks like all the other monochromators. Then there's the slit. Which is, I mean, I guess that's a pretty simple device. And then there's, if you put two of those together, it's a 4-motor slit.
This is the one that we use in our insertion, in our front end slits. So you use this one, this module, on the optics module, or you wrote your own database. You wrote your own database, or you use the one that exists on the one that was. Yeah, but you wrote. Yeah, but did you write your own database, or you used the existing one?
No, we copied it.
Oh, okay. So apparently we could do it.
So there's a mirror, which is almost the same thing as a slit, right? It's just different equations, but it's still a 2-motor coordination.
Oh, wait, so it's a 2-motor. Okay.
It's a two-motor mirror where you just get the average and the slope. And right,
Okay.
it's a slit, really, is what it is. Mathematically, it's no different. Then there are filters. There's a couple of These were for the original filters, I think in the front end. And there's another filter database that was written by a user, actually, that uses the XIA, X-Ray Instrumentation Associates PF4, and gives you a good way to control that filter. That's a pretty common filter.
Can you go back, please?
Yes.
Okay, so it's a motor-driven filter, right?
No.
I don't think it's motor-driven. I think it's pneumatic.
Okay. And can you go into details if you remember what it does?
Yeah, I mean, each one of these guys has four possible
Position?
four possible filters.
Okay.
And you can install all four or any combination of those four to get the
Okay.
filtering that you want. And I think what they typically do is have sort of a binary, right, so that you can get anything you want. And what this user did was to write software that allows you to either one, have very direct control over each slit individually.
And in order to use this work, I have to define the signals different because my signals are different, right?
Not if you buy the XIA PF4.
Oh, it's XABF4, okay. Then.
Right, so
Okay,
it's a commercially available
special-
device.
Okay.
Yeah. So no, you guys could use this directly, and you might already be using this directly because it's pretty popular with the beamline scientists. So you can either control these individually, or you can just tell this software how much filtering you want, assuming that it knows about what the filter, assuming you've configured it so that it knows what the filter types are. So that if you do this as, right, 1.27 millimeters of aluminum is number 4 in this guy, and then at that point you can just say, here's how much beam I want. I don't remember where that's.
There's energy there.
Oh, right. And once you've done that, then this guy calculates all the possible the beam attenuations from essentially none, to basically no beam is coming out, to there's no attenuation at all. And you can choose whichever one of these you want. And of course, that will vary with energy. And then there's another implementation of, no, I think this is still the same stuff. There were actually at 1.2 implementations of this, and I'm not sure if they're still both in there. Then there's the optical table, which is described separately. There is a orientation matrix in here, which was effectively written by Harold Sin when he was working on one of the beamlines that had a whole bunch of crystals, and they needed a lot of like 12 orientation matrices. There's an I0 calculation for ionization chambers that was written by John Tischler.
And this is for which device? Where ionization
This
chambers
is-
are different.
Yeah, an ionization chamber that's filled with a particular gas and controlled by a preamplifier.
We have those.
Yeah, everybody has those. You have to have those because that's how you find out how much beam, the incident beam. That's how people normalize to the incident beam, and that's what this is all about. It's figuring out how much beam it corresponds to the current that's actually read, actually going through that device. Because when the beam goes through there, it's going to ionize the gas, and then the current, it's like a diode, the current will increase. And what John did was to figure out how you find out how much beam is going through there, given the signal that you're getting from the preamplifier. There's PID loop support, which is, I'm not sure what this is actually. I haven't used this myself.
It's just EPID record.
I'm not sure if this is this might be the EPID record.
It looks like it.
It does look like it, yeah.
Maybe for something.
Yeah, I don't know the details of this. So that's the stuff that's in the optics module.
And the soft motors, they are in the
The soft
motor.
motors are in the motor module, but this two-slit database
Yeah, I saw this one.
is, there is a version of this that uses soft motors for the front end. This version uses, these are analog output records, and these are all analog output records, I suppose, which users don't like. Especially spec users, want to talk to motors because spec is really set up to talk to motors. And so what a user asks for is, why don't you just make those things motors instead of making them look like motors, make them actually be motors. And so I try to do that. And that's the two-slit soft database in the optics module.
Okay.
And I think I also did that for the monochromator, but I haven't done it for the optical tables. I don't think I've done it for all the monochromators. I think I might have just done it for one of the high heat load monochromators, because it's kind of a pain. So any questions or comments about the optics module? What's next?
Could you briefly point to where in the motor record all these databases for the soft motors are located?
Yes. Oh, wait a minute, soft motors.
Yeah, the one that we can do coordinated motions.
Right.
With one there.
There
This is
are
only the
some,
slits.
actually, there are some in the motor. The ones that Mark Rivers wrote are in the motor database. The other ones, the ones that I wrote, are all in optics.
Okay, so in the optics module, the one that the record for the slits that it uses the motors is called soft slits. you said?
Two slits soft.
Two slits soft. Okay.
Yeah, let me just go there. So there are 4 of these guys. 4 motors with a D-type soft. Oh yeah, it is. D-type is soft channel. And I don't know if it's really possible to make this clear without like diagrams and stuff,
This is
and
the-
I don't
the
really
one
have.
I just wanted to know the name.
Oh,
Which to
okay.
look for when I need it. This is all.
VDCT is very useful because.
Yeah,
I mean,
and this is a
it's
VDCT
already a
database.
mess, you know, to see it in the VDCT.
Yeah, and I believe this is, this is a VDCT database.
At some point you have to trust people, right? So if you see a
Yeah,
mess,
but
you just have to trust that it's
No, but
working.
it's complicated, even in the VDCT.
It is.
goes
It's a
well.
complicated business, putting
Yeah.
soft motors in front of a motor coordination, because you have to worry about a number of different things. One is that you're writing to 2 different motors, and you have to make sure that you want to know when it's done. And so initially, we just had a calc out record that would listen to both of those guys, both of those motors, and would tell us when both of those motors were done. And what happened was, if the first motor you write to, if you send it to a position that it's already at, it replies that it's done almost immediately. And so there's just a little blip. And for a minute, it looks like the whole thing is done because the first one's done and the second one hasn't started yet. And that got us into trouble. And so in this database, you'll find a gate PV that is opened before we write to any motors and can only be closed by the second motor that we wrote to. And so when all 3 of those things are done, basically, then we know it's done and we don't have that little glitch possibility. So that stuff like that is problems to have to be solved in Epic's database. And this database is reasonably well commented. A lot of databases are not, a lot, including databases of mine, are not commented at all. So I'm not sure what else to say about that,
Oh, okay.
about these things. Or, I mean, I'm basically done, I think, with the optics talk as well.
That really got me confused when I was looking at these coordinated slits, that I think for horizontal and for vertical, I think the extension XP and XN or something was used the same, and it was not obvious, especially when I was writing a gateway access, because probably the slits were, 2 slits were used for 4 slits or something like that.
Right, so the comment was that in the 2-slit database, when you use 2 copies of it, one of them says X, and the other one also says X.
Something like
And that's confusing, and that's because I used one database for both of them. I mean, I used I have a 2-slit database, and then to do 4 of them, I just used 2 copies of that database. And so X and Y it's not X and Y, they're all X. So it's elsewhere in the PV name where you find out whether this is the vertical slit or the horizontal slit. So I think the only thing that's left is state notation language. I think it's.
Can you go also and show where the databases for the one coordinated motion is located for the motors? Like if I want to use the one.
Oh, that's the database that.
In this one.
That was the database itself. Yeah.
Yeah, but this is for the 2.
No, it's just for two leaves. It's a 2-slit, right? And so we use 2
Oh.
copies of that database.
That's complicated for 2.
I know. It's not 2 slits. It's 2. Yeah.
I see.
Right.
I see.
It's 2 motors, and that's why it was
Motors.
2-slit.
I
Yeah.
see.
Yeah.
Okay. Then I'm reconsidering. Maybe to do it in the